Hi everyone. Today we are going to do a little, let's say, introduction of chapter 8 numerical methods. Normally numerical methods is a whole semester class. So I'm going to introduce you to three different methods which are kind of similar in some ways. And they are going to be like sections 8.1, 8.2 and 8.3, I think. I'm going to start with Euler's method. So what is the idea? We are solving equation of the first order or something like this. dy dt equals f of ty. Of course, if you can solve it analytically, you're fine. You just find the formula, right? But you know, sometimes you just cannot integrate it or just cannot solve it analytically. Initial conditions. So what else we can do, guys? Well, we can take our interval of interest. For example, starts at point t0 and goes to some point b and divide it into n subintervals, something like this. And on each subinterval kind of like set up name for the end of subinterval, like over here, for example, T1 and then T2 and so on, right? Well, because we are dividing on equal subintervals, which is not necessary for the method, but we are going to do it just to make it simpler. We're going to introduce a step. H is going to be a step. In our case, it's going to be equal to what? B minus T0 over number of the steps. I'm going to use both like t with index and like the steps. So I'm going to label, for example, t1 equals t0 plus h. Okay. Now, what we can do, guys, if you kind of know initial conditions, the value of y at t0, well, we can just graph it at t0, it equals to some y0, somewhere here, some y0. So you do know the first point of the function. You also know that derivative at this first point, if you plug in this y0 instead of y and t0 instead of t, you are going to have something like this. dy dt equals f of t0 and y0. So you basically know in which way function goes from the point, right? You know that derivative is a limit, right? But limit of what? What is dy dt? dy dt, it's a limit of delta y over delta t, right? When delta t goes to 0. Well, let's imagine that it does not go to 0. It's just staying some value. I'm going to, instead of delta y, use kind of the change of the function from t0 to t1. So I'm going to write down, imagine that's y1 minus y0, and over here t1 minus t0. Normally, we're supposed to bring like t0 very close to t1 or t1 to t0, and kind of it's going to be a limiting process. You are going to get the exactly derivative equals to this. But we can say that this derivative, that's approximate derivative, approximation for derivative, is equal to the value of the function at t0 and y0. Now, what is this? Well, because I already kind of said that I'm dividing on equal intervals, t1 minus t0 is going to be my step. So I can write down that y1 minus y0 equals approximately f of t0, y0 multiplied by a step. Now I can calculate or solve it for y1. y1 equals y0 plus f of t0, y0 multiplied by a step. Well, what this equation gives to me, the value of y at the next point t1. Well, for example, it's going to be somewhere here, y1. And while using a similar formula for y2, just instead of y0, plug in y1, we can get like more points. So these points are going to be estimations of the solution. And this is basically the idea of Euler's method. We estimate solution using like derivative and kind of trying to predict what's going to be the value of the function on the next point. I'm going to write the general formula for Euler's method. Let me change the color so I can still keep it on the same board, but like general formula. So general formula, yi plus 1 on the next step equals y on the previous step plus function at the previous step I multiplied by the step. And if you kind of have unequal steps, it's supposed to be multiplied by the distance from the previous step to the next step. In your case, it's going to be like y plus 1 minus t. Let me write it down, I plus 1 minus ti. If your steps are not equal, you can kind of do these calculations. Well, that's basically, that's kind of general formula for Euler's method. How good is it? Well, it's not bad. We are going to see, I'm going to have a demonstration how good the method is working. What are the ways to improve it? Well, the best way to improve it, of course, to make smaller steps, because smaller step delta t is going to bring this ratio closer to actual derivative, which is equal to the function. So, of course, smaller steps are going to help us to make it more precise. So this approximate statement is going to be more precise if this T1 goes closer to T0. Well, there are pluses and minuses in making smaller steps. If you are planning to cover a certain interval, smaller steps are going to cause you to do more steps. And because on every step, this equation is not exact, you are going to kind of have a small error accumulated. And more steps you have, more of these small errors are going to accumulate it. So there's always a balance between like number of steps and the size of a step. Of course, the best is to do the step as small as possible, but of course, number of steps is going to affect like accuracy of solution too. And the second, remember, each step is going to require some computer time to do. And like you cannot do infinitely many steps. You're supposed to stop somewhere. And like more steps, more computer time to kind of spend on this, right? Well, the formula is pretty simple, so it's not gonna not gonna take a long time, but just like general idea, right? That there is always a balance between size of the step and like how many steps do you want to do, because like going in this direction is going to affect accuracy in both ways, make it better because the steps are smaller, but make it worse because number of steps is bigger. Euler's method is a first order method to like in considering of accuracy. Means that, for example, if you take a step equals, I don't know, 0.1 and then decrease it twice, the accuracy is going to increase like proportionally. So 2 times. I'm going to talk a little bit about errors and accuracy, but first I want to introduce like 2 more methods. There is improved Euler's method and Runge-Kutta method. I'm not going to go too deep into theory. I'm just going to kind of explain it very, very simply. So let's move to improved Euler's method. And then I'm going to kind of talk a little bit about errors. I don't want to go too deeply into errors. Give me a second. I'm going to do improve. So how do we improve Euler's method? This is like, I think 8.2, but I'm going to just call it improvements. Improved. Well, if you write down equation y prime equals f of t y, right? And integrate it on both sides. Put integral here and put integral here and integrate it between ti and ti plus 1 on one step, along one step. And here ti, sorry, and ti plus 1. Well, here, because like integral and the derivative are going to kill each other, we are going to get solution at point ti plus 1, according to Newton-Leibniz formula, minus solution at ti, right? What are we going to have over here if we integrate? Sorry, I don't fit dt over here, but we do mean actually dt here. I'm going to make it small. What are we going to here? Well, we would integrate it if we do know the function, right? We do know the function, but for this function, we actually know only t's. T's are kind of known for us. It's just like free variable. But y's actually are calculated through the equation. So we don't know how the function actually looks. So what we normally do, we are approximating the function. Well, the simplest way to approximate the function is just to put a constant instead of it. I'm going to draw a picture. Like for what we do for approximations. Well, I don't know how the function looks, but let's imagine the function looks like this. This is ti, this is ti plus 1, this is t, and this is y. That's my actual function. So that's actual, like, well, I'm going to label it f of t, y. That's my actual function. Well, we don't know why, so we don't know really how it looks. One of the ways, well, what we are doing over here, we're finding the area under the curve, right? One of the ways to estimate this area under the curve, which we need this area, right, is to kind of put a constant over here instead of actual function. Let me just kind of change the color. If we do a constant like this, well, that's going to give us some estimation, right, of the area. So what we can do, we can write out f of ti yi, which is going to be this number, right? Multiplied by the size of a step. I'm going to call it h, but you can always write down t I plus 1 minus ti. And that's going to be what? Our Euler's method, actually. If you move this one over here, you are going to get like y on the step ti plus 1 is going to be equal y on the step ti plus f of ti yi, right, multiplied by h. That's Euler's formula. How else can we kind of improve it? Well, if the function looks like this, makes sense probably consider it as a trapezoid instead of like a rectangular approximation. A trapezoid means like this. Connect these 2 points and treat this area like this area. I don't know which way to cover it like this. Okay, I'm going to cover it in pink. Well, the area of trapezoid is a little bit different, right? We need to do this side plus this side divided over 2 and multiply it by the distance. So I'm going to write it down. Well, I don't want to move this one again back like to the left side and then to the right side. So I'm going to just kind of improve the integral part. So this part is going to be improved. I'm going to write down the part which does not change, y of ti. And then what is going to be improved part? I'm going to write down that's f of ti yi, this side, plus f of ti plus 1 yi plus 1 divided over 2, right? Sum of the sides and multiplied by the height, which is still h. Well, improved formula looks better, right? Gonna give us better accuracy. The only bad thing here is that we do have the very same I on the next step, this one, which we are trying to calculate. And this is not good. So I'm going to maybe kind of mark it that this one and this one, same. Well, we cannot use unknown number to plug it into the function and calculate this unknown number. This is bad. What we can do, guys? Well, why don't we use the previous formula for these numbers to predict it? Because this formula is not using anything unknown or illegal. So why don't we use it? So why don't we use for y, I plus 1, this one? And that's going to be improved Euler's method. I'm going to write down the formula for improved Euler's method. So it's y I plus 1. So this is like t plus 1, but I don't want to copy it. It's yi instead of this one, right? Plus, how about I write down step over 2 in front and then put this in parentheses. So f of ti yi, and we do know them from the previous step, right? To calculate next step, we do know what is t and y. Well, we know t for all the steps, plus f. We do know what is ti plus 1. this is just ti plus h, right? Plus one step. But instead of this, we are going to use this formula. So I'm going to write on yi plus f of ti yi multiplied by a step. Very nice formula, right? Looks a little bit kind of weird, right? We do have function f sitting inside of the function f, but at least we don't have anything illegal here, right? All the numbers from over here we do know from the previous step before we move to the next step. Well, guys, what are we going to do just for future? Because I'm planning to use a similar formula for Runge-Kutta method. I'm going to label my numbers a little bit differently. So I'm going to label this. Let me change the color. Which one I did not use yet? Let's go to blue. I'm going to label this one as K1I. Well, I because it's a step I. At K1 it's just like just the first coefficient. And I'm going to label let's say I was thinking like this one, the whole thing as K2I. So to write down this formula short, it was not supposed to give me this thingy. Yeah. Okay, I don't know where to put it, but I want to write down one more formula. Maybe over here. yi plus 1 equals yi plus h over 2 k1i plus k2i. Coefficients, which are defined like through these two formulas, and just a shorter way to write it down. This is improved Taylor method. Now, guys, improved Taylor method gives better accuracy. Accuracy of this method is h squared, so proportional to the step squared. So actually, if you kind of change step twice, you are going to improve it like 4 times in comparison like to Taylor's method. So a little bit better. But there are methods which are giving better accuracy. I'm going to just, without explanation, give you a formula for Runge-Kutta method. Runge-Kutta method is fourth order method. This is second order method. Taylor's method is first order method to the size of the step. Runge-Kutta is a fourth order method. Well, you know that this unknown function is not necessarily supposed to be approximated by a constant or by just a straight line, right? We can use other polynomials. We can use quadratic polynomial, cubic, polynomial of fourth degree. So, well, we are using a next polynomial, and the formula is going to be slightly different. So, Runge method. I'm just going to give the formula. I'm not going to obtain actually it like I did the previous one. So I'm going to say that y on the next step equals y on the previous step plus h over 6. Remember we had h over 2 for the previous one. And there's still going to be coefficient. Coefficient 1i plus 2 coefficients of 2i plus 2 coefficients of 3i and plus 1 coefficient of 4i. You see that like we are trying to approximate function or predict what is the value of a function on this interval by using different polynomials. I think we are using like quadratic polynomial for Runge-Kutta. I'm not sure, like 100%. I remember that it looks like a parabola, but yeah, I think we're trying to approximate by quadratic polynomial. But okay, right now it's not super important. We're just using the better approximation. And Runge-Kutta method is going to give us better error. What are going to be the constants? K1, K2, and K3. I'm going to write them down. So K1i is still going to be f of ti yi. Well, just like in the previous method and just like in Euler's method, f of ti yi k2i. Now, it's going to be a function on half of the step toward the next t. So 1/2 step here. And for approximation of y, we are going to also use like 1/2 step approximation. 1/2 of h k1i. You see that this k1 goes over here, multiplied by the step. Well, that's just a function, right? So if you that's the function multiplied by a step, but because we are estimating it in the middle, we're doing like half of this prediction. So normally like the full step is going to give us me a step by a function, but half is going to give me a half. 3i is going to be f of ti plus 1 over 2h again, similar way yi, and I'm going to use my next k, like my better approximation in the middle, 2i. And the last one is going to be just a full step for I. And again, Runge-Kutta method is a fourth order method. H yi plus h k 3i. More complicated formula, but not that super complicated, kind of natural. So this is the first step, this is the last step, and there are two steps in the middle which are trying to do better estimation. Why do we have 6 here? Let's count how many constants we have here. 1, 2, 3, 4, 5, 6. 6 constants actually added, so we divide by 6, kind of trying to find average, but like better average of the function, or better integral under the function. Okay, now guys, I want to consider an example, and I want to consider an example which I can actually compare to what we are going to see on my graphs. So I'm going to consider equation example. I'm going to consider equation y prime equals y plus t and y of 0 equals 1. Very simple equation. I'm going to solve it as like just like we normally do, right? Homogeneous equation is going to have solution y homogeneous is a constant c e to the power of t, right? Kind of guessable, right? Particular solution, because it's t, right? We are going to have it's a t plus b, and we just need to plug it and calculate a and b. So I'm going to do it, and that's going to be actual exact solution. I'm going to use the very same equation to see how exact solution compares to Euler's method, to improved Euler's method, and Runge-Kutta method. That's going to take like 10 minutes probably. To calculate AB, I'll need to differentiate it. So I'm going to get A as a derivative, right? And here AT plus B plus T. So what I see is that A plus AT plus T is supposed to be equal to 0. So A equals what? Minus 1. And B here is equal to A. So looks like that's also minus 1, right? So B, no, B, sorry, B equals to, yeah, supposed to be minus 1 too. Let me double check it. Where is my solution actually? I can just have a solution made up. No, there's supposed to be somewhere T. Maybe I'm missing a number. No, that's just, they're both equal to minus 1. Okay, so I'm going to have a solution, particular solution is minus t minus 1, right? Now, because it's initial value problem, I'll need to calculate the constant. Well, if I'm planning to graph anything, I cannot graph with arbitrary constant in it. So my total solution is going to be what? C e to the power of t minus 1. Somehow I thought that's plus t. Now I'm going to plug in 0 here and kind of find the constant from initial conditions. So it's going to be C. If I plug in 0 here, it's going to give me 1. 0 here is 0 minus 1. So what I have actually is that C equals minus 1 goes over here, gives me 2. So my exact solution exact solution is y equals 2e to the power of t minus t and minus 1. Now I'm going to kind of try to do some calculations for Euler's method, improve the Runge-Kutta. What I'm going to do, guys, I do know that it's very easy to write down like these calculations in some programming language like Python or I don't know, like C++. But I don't know like if everyone in class knows them. So I'm going to use Excel. It's not the best way to do it and not the best way to graph it, but you know, everyone can learn it. So what I'm going to do, guys, I'm going to create a table in Excel. And in the first column, I'm going to put the value of my t. And I'm planning to use step h equals 0.2. So my first value is 0, my second value is 0.2, 0.4, and so on. Here I'm going to put exact y, exact y. Well, exact y can be calculated by plugging in t here, right? I'm going to use the formula here, and kind of instead of t, I'm going to plug in the cell. I'm going to substitute cell which sits over here and cell which sits over here and kind of calculate. So I'm going to use the formula exact solution. Next one, I'm going to do improved Taylor. Remember, for improved Taylor, I'll need K1 and K2. So I'm going to calculate K1 first, and then K2, and then improved Taylor. Oh, no, I did not do Euler yet. Okay, sorry, rushing too much. So let me erase this and go back. So my next one is going to be Euler. For Euler, my Euler doesn't look like Euler, right? Just one more time, try to write down Euler solution. So for Euler solution, that's just like the simple formula, right? You take, you start with 1, and for the second step, which is going to be like, if this is y0, that's going to be y1, right? You are going to have y0 plus the value of a function, like this one, that's my function. So I'm going to maybe label that my f of ty here is equal t plus y, very simple function. So the value of function multiplied by a step. And I'm going to show it on Excel file. Then next one, I'm going to do k1 for improved, k2 for improved, which are also calculated through the function. And then I'm going to do improved. Next one, I'm going to do k1, k2, and k3 and k4 for Runge-Kutta, and then I'm going to do Runge-Kutta. I'm sorry, I'm running out of space here. Maybe I should stretch a little bit more my whiteboard. Somehow it gave me a shorter whiteboard this time. Oh, okay. So now I can write down Runge-Kutta normally, right? Let me just make it like a bigger cell, Runge. I'm going to call it Runge. And again, each one, I'm going to start with 1. The first number for Euler, for improved Euler, and for Runge-Kutta is 1. The second one is going to be a formula. Here for Runge-Kutta, formula is going to depend on these first values. For improved, the formula over here is going to depend on these two values. For Euler, well, I'm just going to plug it in the formula. That's going to be the formula. And for exact, the formula is this one, right? I'm going to just plug it in. Okay, now let me show you what is going to happen. I'll need to do the new share, I guess, move to my Excel workbook. Okay, I don't know, my computer does not make any sound, but just in case, share. So yes, that's what I did actually. Maybe I should increase a little bit this side to kind of show what is going to happen. So how did I build the table? Again, I put my t's over here. You see the step is 0.2. How you can do it? You put two first numbers and then you kind of do this and stretch it down, and that's going to automatically fill the rest of them like this. Well, I did it from 0 to 4. You can do as many as you like. For exact value, I put a formula here. So I just literally entered 2x for E, A2 is going to be the value of T at 0 minus A2, which is also T, and 1 is going to be just like subtracted 1. And that's going to be exact solution. Now for Ehlers, as you remember, the first one is 1. And for the second one, I do have a formula. My formula starts with the first one, which sits in the cell C2, and then combination. This is a function, right? My function is y plus t. So my y is C2, and my t is A2. And I multiply by my step 0.2. Yeah, there is easier way to write it down. Just set up step as h somewhere here in Excel, but I don't have time for this. And then you just can stretch this formula down. If this is filled, it's going to fill automatically the rest. Just like take the formula and stretch it down, it's going to fill automatically all the cells. Now, for improved Taylor, I have K1 and K2. First, I start with 1 over here, and then I calculate K1, which is just a function again. So A2, which is T, and F2, which is actually my Y, right? And K2 is a little bit more complicated, involves the steps. You can look the function, right? And again, I kind of stretch it again, all this, like as soon as I feel this two, I'm going to stretch this one down, and this one down, and kind of this one down. So I'm stretching like all of them down. Well, if you stretch one down, it's going to give you this, the one everywhere, right? But here I'm entering the formula, which depends on K1 and K2. So this formula is working with these two numbers, not this next two, but the previous step, right? And then what I'm doing, I'm kind of creating two more here by stretching this one down and this one down, and then I stretch all three down here and get like some values. Now I'm repeating the procedure for Runge-Kutta method. Just Runge-Kutta method has K1, K2, K3, and K4, and I do the formula, just like I kind of calculate it as a separate table, but I put it together with this. Start with 1, right? And again, this is the formula for Runge-Kutta method. You see division by 6 over here, right? Division by 6, and 0.2 is my step. And K1, K2, and K3 are sitting in cells G2, H2, I2, and J2. If you look over here, you can see them G2, H2, I2, and J2. Okay, then kind of I stretch these formulas one step down, and then I stretch all the whole thing down there. Well, that's going to be like calculations, right? I'm going to show you what we have at the end. At the end, we are going to have exact value 104, Euler's formula 71, better prediction from improved Taylor, and better prediction for Runge-Kutta method, though these two are not super different. Now, let me show you the graphs. So what we have on the graphs, I'm going to make it smaller, sorry. On the graphs, we have a comparison. The blue graph, the top one is exact solution. The bottom one is Euler's method. And the two middle ones, you probably cannot see that there are two, but there are two of them, are going to be improved Euler and Euler's method. Well, what I can do, guys, I can attach my Excel file to like the module on the web page on Canvas, so you can kind of play with it. Maybe I did a mistake somewhere. I did not try very hard to kind of check all the numbers, but everything looks kind of good for me. Okay, so that's like how we use the methods. Now, just 2 words about errors. Let me go back to, like, you see that, well, basically solution is good, but not that like super good. What we, okay, guys, give me a second. Okay, a couple of words about errors. So what do we have, guys? We do have like error on every step. Error on every step. Well, and that's going to be the difference between actual value of a solution, like actual solution at the step, like at the point T1, minus a calculation or numerical approximation. So that's actual solution. And that's what numerical approximation gives us. Numerical numerical approximation. Okay, this is called global truncation error. Okay, major sources of global truncation error. Well, approximate formula. Well, we do use approximate formula. We're trying to approximate actually this integral by different formulas, and like Euler's method and improved Ehlers and Runge-Kutta are introducing different formulas. So the formula is still approximate. It's not correct, right? Second source is approximate values of like y from the previous step. The previous step already has not correct y's, which we plug into approximate formula and get even better error. Another source of errors is round-off error. Round-off error is arithmetic error, which comes because computers are usually don't keep like infinitely many digits when they keep like numbers, right? They round it up. So let's say actually we're going to have not exactly numerical approximation, but some kind of computed value, which is not going to be like, which is going to be also truncated by a computer, right? So I'm going to kind of write down around round-off error, and that's going to be something like this. Give me a second. It's going to be yi, which we're supposed to calculate if we had computer with infinitely many digits, keeping all the numbers in our numbers, and the actually computed value y. So this is what we're supposed to have if we have like infinitely good computers, and this is computed value. Well, because like if you deal with numbers with certain amount of digits, you add them, subtract them, you do rounding, and that's going to give you slightly different number from what you're supposed to have if you kind of don't limit yourself to anything. So generally speaking, we are going to have a solution at point ti minus this computer calculated solution, right? And this is going to be actual error which we are going to see, and this error is going to consist out of like our formula errors, which are going to be like these ones, the first ones, and our round-off error. Sorry, minus yi. Well, that's going to be like what the error we are going to see. Well, error due to the formula is called local truncation error. Local truncation error, usually I'm going to label it little I, EI. Local truncation error can be estimated, and it's usually proportional to second degree of the step divided over 2 and multiplied by m, where m is a maximum of a second derivative. M is a maximum of absolute value of second derivative of our actual solution on interval AB, on interval where we solve it, right? Global truncation error on interval is approximately going to be like, well, each step is going to produce this error, right? So if you are in step 5, you probably are going to have like 5 of these errors added. So I'm going to put I here and the formula over here. Number of steps usually is proportional to like size of the interval and the size of the step. So if your size of the interval is AB, so we are going to have like B minus A divided over H. That's going to be number of steps, right? Number of steps. Well, I is like somewhere like within this number. So I'm going to say that it's proportional to 1 over H. So together, they're going to make up M H over 2. Or global truncation error is going to be proportional to the step. And this is going to be like for Euler's method, just proportionality to the step. Improved Euler's method is going to make it proportional to the step square, and Runge-Kutta method to the step to the power of 4. Okay, well, I think that's all. Guys, can you try to read? It's very hard to squeeze like 3 sections into one like normal lecture, especially that it's not supposed to be 3 sections, but a whole class of discussing of how these errors are estimated and how the formulas are obtained. So can you look at least through sections 8.1, 8.2, 8.3, just like to see a little bit more text on the topic, okay? And I'm going to attach my notes, which are not looking very nice, and my Excel calculations. I'm thinking to ask you to do as extra credit some kind of first order differential equation and try all these 3 methods. Without very good theory, you still can use the methods. And just I want to see like if you can kind of deal with these numerical calculations. But again, I want to introduce it as an extra credit. I don't want to give it as a normal like, credit. Okay, I think that's going to be all. And we are going to stop at this point.